Welcome to Advanced Reverse Engineering. Let's talk again about some tools. And let's talk about the bashrc.sh script that's available to you from the class page. You can go and find this in the extras section of the content on iLearn, along with some information about it. There's actually, if you go to the GitLab page for it, there's some, I think there may be some more stuff there, although what's there may have changed. It's undergone some changes since it was distributed to the class. So I'd go with what you get off of the iLearn page. The idea is that within your bashrc or your zshrc files, these two files, depends on which shell you use. If you use bash, if you're just doing the default installation of Ubuntu, then you'll be using bash. Some people really get super cranky and want to use a ZSH. So if you do that, use this. But for the most part, bashrc. And what you'll do is, within the bashrc, at the end of that file, you'll add a line that says source, followed by the name of the script. And once you've downloaded it and put it somewhere, you'll source the script from wherever you put it. For example, if you put it in your home folder, it'll just be source bashrc.sh. And what it does is adds a few aliases to your shell, a few additional, essentially, commands to the shell. These have to do with disassembling code, but this last one, MK, is one we'll use a lot. The weird cryptic lines you've seen at the start of program samples, those are make instructions that tell you how to build and compile or assemble and link the file. And make is a way to automatically do what's at the start of the file like that. So, for example, if you see this little line up at the top of this file, what the heck does that mean? Well, the semicolon just means it's a comment within this assembly, right? Semicolon is how you start a comment inside NASM assembly. It's not true for all assemblers, of course. If you're using the GNU assembler, it would be the C style or C++ style comment. But in NASM, it's a semicolon. So this just means this is a comment, so the assembler doesn't see the rest of this. The script looks for these three characters, MK:. That's it. It looks for those three, and when it finds those three, it takes everything from this point over and interprets that as a shell command. So, in other words, what's going to happen is the shell is going to be given this. Now, what is this? Well, the $sign indicates a variable, and the make script defines some special variables. It defines make AS in such a way as to assemble the content of the file, and it defines make GCC in such a way as to link the content of the file. So this says assemble and link. Now the little 2 ampersands here, that's a bash thing, and what it says is if the previous command succeeded, if the return value of this was 0, then do this. So assemble, and if the assembly phase works, then link. But if the assembly phase does not work, stop. Okay, pretty straightforward stuff. There are a lot of different variables that are defined by it, but the important ones are things like this. Make AS assembles, make LD links using LD, make GCC links using GCC, which calls LD, but it does it after wrapping your code with some other stuff. Make file is the file name is the name of the containing file. So if I want to know what the file name is here, I would put it up here. So for example, I could test that by just replacing this command with echo $make file, and it would, when I did a make on this, it would just print out the file name. Make base is the same file name, but with the extension removed. So if this is foo.asm, then make file would be foo.asm, and make base would be foo. And that's important because sometimes I want to specify the output or the final result, and I need to replace the file extension with something else. If you're curious about all this, you can run make with --debug, and this file name, and it won't do anything, but it will show you what all the variables are set to and the command that it's going to execute. Here are some other examples. This is probably the most common. Make a symbol and link. Make a symbol and link with GCC. This is a little more elaborate. So what happens is this assembles the file, and then if that worked, it tries to link it with LD. If that fails, that's what the little OR here does, then it tries to link it with GCC. So this is a really odd thing. I don't think you'll ever see that, but it gives you an example of some of the stuff you can do with the bash connectives, the ampersand, ampersand, and the two vertical bars. This line says to assemble, try to link it with GCC. If all that works, remove the intermediate file base.o. So just the RM, and then there's that base we talked about before, which is the file name without the extension. I put a .o on the end because that's the intermediate thing produced by assembly. This cleans up a bit after itself, assuming that everything works. So let's get back to introducing assembly. Now that we know how to build assembly stuff a little bit, let's talk about how to actually do assembly. And over the years, assembly languages, there are lots of them, have sort of grown toward a common way of expressing what you want to do. And so we'll talk about some of the variation and commonality in assembly languages. So each processor has its own machine code, its own way of interpreting the bytes that are in memory as instructions, and consequently it has its own assembly language. And so if we take a byte sequence like 08EF90, well, that's just 3 bytes. What does that mean? Well, the interpretation depends on the processor, and sometimes on other factors as well, but mainly on the processor's language. And so if we're over here on the x86-64, 08E5 is a single 2-byte command. It's OR of these two registers, AH and CH. Okay, registers are just named storage in the processor. And these two are named storage that consist of a single byte. And then 90 is a no-op. It's an assembly instruction that performs no action, except, of course, advancing the instruction pointer and wasting some cycles. Okay, so it says, don't do anything here. Just go on to the next instruction, like pass. So over here is the Motorola 68HC11, which is a microcontroller based on the 6800 series of Motorola controllers, which, by the way, is the first microprocessor I ever wrote any code for. And 08 is increment X. So this is incrementing a register called the index register, which is 16 bits wide. And then E590 is interpreted as bit B of 90 and X. So this is a bit test. This is ANDing the contents of, in this case, memory, and the register B, which is an 8-bit register, together. X is the index register. It provides the memory address, and this is an offset into memory. So there are various dialects of assembly language. So those were two very different assembly languages, but there can be dialects of the same assembly language. For example, on Intel, we can have this string of bytes right here that turns into sub RSP and 8. So this says subtract 8 from the content of RSP and store the result in RSP. This says go and into memory to the location of the instruction pointer, add this offset to it, take the contents of memory at that location, and put it in RAX. Okay, that's what those two do. They do the same thing over here, but they're represented differently in the AT&T dialect. So over here where we have 8, and we subtract it from RSP and store the result in RSP, have the same thing over here. We're again taking 8, subtracting it from RSP and storing it in RSP. You'll notice that over here we just have the register name and a literal for the Intel syntax, But over in the AT&T syntax, we put a $sign in front of the literal and a % sign in front of the register. Just a little different notation. The move is also quite different. The order is clearly reversed, but in addition, the way we represent the location, here it's RIP plus an offset. Over here, it's an offset, and then we have it indexed by this variable RIP. So we can sort of think of this as the location and this as the index, which is really the same thing as this. It doesn't matter because, again, addition is symmetric. So each assembler, in addition, so let's say we're just sticking with a particular syntax, just Intel syntax for the x86 64. Even then, there's differentiation. Each assembler, there's NASM and YASM and MASM and a whole bunch of others. Each assembler has its own directives and macro language and special syntax. And this is also, confusingly, true for every disassembler. So a disassembler might see it's not going to have the same directives as an assembler, but it will look at an instruction, which maybe loads something through a special table, like the program linkage table. And when it decodes the instruction, it will try to display that information for you, but it will display it using its own syntax, which may differ from what the assembler has. Or many disassemblers will show you an instruction with arguments, even though the instruction doesn't take any arguments. They do this to make clear that what's happening. Some arguments are implicit, and the disassembler will show you them as if they were explicit arguments, even though they are not. So there's lots of things like that happen. Here's an example of code. On the left-hand side is assembly code for NASM. On the right-hand side is assembly code for the GNU assembler. You can see the highlighted line here. I've told it I want the Intel syntax with no prefixes. And so now I basically have the same dialect chosen in both, but you can see there's still some differences, right? The directives are different. Over here I'd say global, but in the GNU assembler I say .global. Extern becomes .extern. Section.text becomes .text. Section.data becomes .data. And you can see down here at the bottom, the message in the NASM world is data bytes, hello world, comma 0 for a null terminator. Whereas over here in the GNU assembly, it's a .ASCII Z terminated string, the 0 terminated string, and it's just hello world. And the assembler knows to insert the 0 for me because of the type I gave it. There's even some stuff within these instructions. So for the most part, look the same, push RSP, move RSP into RBP. Then we have this load effective address of RDI and then this relative message. Over here that becomes message plus RIP, which is what this means, and it's just a little more explicit. Then I have call putS with respect to the program linkage table. Over here it's call putS at PLT. So some subtle but tricky and important differences arise depending upon which particular tools you're using, and you just have to be ready to absorb that. So it's important that you understand how these different things work and what they mean in order for you to understand what the different tools are showing you. If I assemble them, do I get the same results? Well, here's the assembly using NASM, and here's the assembly using the GNU assembler. And if we look at these, 544889E5, 544889E5, they give us exactly the same bytes. It looks like they produce identical machine code, and that's great. But you have to keep in mind that assemblers actually generate other information. They'll generate something called relocations, and we'll talk about those later. And these things can differ slightly. They may put notations in the code. They may put commentary in the file itself. And all those things can be different. And if you take these two files and you just do a straight binary diff on them, you'll find that they differ. And we'll cover linking relocations later on. So there's a lot of commonality in assembly line. You've seen a lot of differences. Let's look for some common elements. So there's a lot of commonality here. Some of this comes from just the way we've settled on doing assembly and machine code. Some of this comes from higher level languages that have pushed demands down on assembly to mirror some of the structures in the higher level languages. So we've all sort of agreed on the fetch, decode, execute cycle. That's just how these modern processors work. An instruction pointer or a program counter that determines the location of the next fetch. Control flow being handled by conditional relative branches or by unconditional jumps. That's not true of all modern processors, by the way. Some processors actually let you encode information about conditional jumps in the instruction itself, but we won't worry about that. A simple subroutine system where the return address is usually pushed on the stack or held in a register. So on x86, you will push the return address on the stack. That's the most common way to do it. On ARM, you have a register that holds the return address. Now, what if I have another subroutine call? I'm already using that register to hold the first one. Well, in that case, I have to push onto the stack. So putting return addresses on the stack is pretty universal. Registers are named storage that hold intermediate values and control the processor. A stack used for local variable storage and usually for subroutine return. Everybody has a stack. Some have really depend on stacks. They're stack-based assembly languages. And there are some high-level languages that are really stack-oriented. Forth, for example, is a high-level language that really depends on the stack. Programs can directly reference memory by address, and they can use primitive types. And there's a condition register that contains flags that are modified by the instructions and can be referenced later for conditional branching. Bit-oriented operations are going to be super important. So you may be aware of them from C, but not care much about them. They are the way you do a huge amount of stuff in assembly. They are the key to understanding most assembly programs. Rotate, shift, and or not. Those are all going to be really super important to you. It's convenient that the program counter always point to the next linear instruction because that simplifies calling and returning. So, I mean, think about that. If it always points to the next linear instruction and I hit a jump, I just replace the value. If I hit a conditional jump, I only replace the value when I want to go somewhere else. Otherwise, I'm already pointing to the next instruction. Very simple and very easy. When I call something, I just load the value. I store the current value, I load the new one in the instruction pointer, and I go there, and when I return it, I come back to the next instruction because that's where our IP was. It just makes life easier. That's not the way it's always been done. The 6502, which is a very famous processor used in the original Apple computer, and I think in the original, I think 6510 was what was used in the Commodore. It had to waste some cycles because when it stored the program counter on the stack, it did it off by 1 and then had to increment it on return. It's a common convention that the stack pointer points to the last item pushed on the stack. And again, the 6502 doesn't do that either. It points to the first open address. But it turns out that over the years, we've sort of settled on this notion, this general notion that we'll talk about again, of when you have an option between two addresses, right? I can point to the last thing pushed, or I can point to the next open slot. I can point to the last byte of the program, or the first open byte after the program. I can point to the current instruction, or the next instruction. I will choose the higher address of those two. And so you sort of internalize that, and that's a good model for almost all modern processors. Let's talk about instructions, operands, and addressing modes. Now we're actually getting into the nuts and bolts of assembly. A lot of commonality. They follow the same basic format. You've got a mnemonic. In this case, it's move. Move is the most common mnemonic you will encounter in programs that you look at, period. Move is going to show up all the time. And what move does is it copies a value. So in this case, it copies the value 1 and puts that value in RAX. So after this instruction executes, RAX, a named register, named storage in the processor, holds the value 1. Most mnemonics are fairly obvious once you've done a little assembly, like mov. What is that? Let's move. And you'll remember it as move. add and sub are good. Some are not so obvious, and we'll see a lot of those. Some are very specific to certain cases and have really weird names. And, those are just the names they have. Operands are basically the arguments to the instruction. They are positional. The position matters. x86 uses the order destination source. And in fact, that is a very, very common ordering among processors. ARM does the same thing. It may have more, but there's still the destination is the first one given. And if you sort of think of there being an equal sign where the comma is, it makes sense, right? RAX gets 1 or RAX equals 1. That's what's happening here. And that order makes so much sense that that's what most assembly languages use. It's not what AT&T uses, but that's okay. There can be explicit arguments like we have right here, and there can be additional implicit arguments which aren't given there but are used. So again, destination source is the order, and you can think of it as assignment. Here are some different instructions that take different numbers of operands, and let's see what's going on here. So clear carry clears the carry flag. The carry flag is a bit in the condition register which tells whether or not the last operation resulted in a carry or a borrow. So think about adding numbers. When I add, let's say, 2 3-digit numbers, I might have a carry, which means that I would need to put that in the 4th place. And when I subtract 2 3-digit numbers, I might have a borrow there that indicates I would need to borrow something from the 4th place. Well, the same thing is true here. Carry just means that I either had to carry or borrow a single bit in the binary representation of the numbers. RET16, this is an instruction that can take 0 or 1 operand. So basically it has 0 or 1 argument. If it's just returned by itself, that's mostly what you'll see in the 64-bit assembly code, and it just means return to the address at the top of the stack. It will have an argument often in the 32-bit world. The argument has to do with passing information on the stack, and ret with a number allows it to return and also deallocate a part of the stack. We might talk about that a little bit later on. Inc takes a single argument, the thing to, in this case, increment. In this case, it's the 32-bit register EAX, and it basically adds 1 to the values stored in EAX. Think about this. If EAX overflows, if it's at its highest value and I add 1 to it, all those 1 bits will become 0 bits. It will overflow. That would mean I would have a carry. All the bits would be 0, so I'd have the 0 flag set, etc. So you can think about how these all work. But in this case, it always takes 1 argument, which is an address or an address in memory location, or a register to increment. Add takes 2. So in this case, I would take the 32-bit contents of EAX and EBX, I'd add those together, and I would store the result in EAX, right? So this is like EAX plus equal EBX. IMO can have 1, 2, or 3 operands. In this case, it has 3. Here it says, take EBX, multiply it by 7, and store the result in EAX. And that's great. But as we'll see later on, we could do it with a single operand or with 2 operands, and it would have different meanings depending on that. MoveSB is a string-oriented instruction. It takes 3 arguments, and in this case, they are all implicit. And this is moving a string byte by byte. It needs a source register, which is RSI, a destination register, which is RDI. It needs a direction flag, which is in the condition code register, etc., to make all of this work. Now, if I take the stuff up at the top here and I assemble it, and then I go and disassemble it with objdump, I'll see the stuff at the bottom. So some of this is pretty obvious. ret 16 becomes ret with a hex 10 because hex 10 is 16. These all look the same, but this, look at this. This has what appears to be a byte pointer to RDI, a byte pointer to RSI. It seems to have two arguments separated by a comma. It does not. And instead of being move SB, it's become move S, and the B has come over here and become part of the byte pointer notation here. This won't work. You can't assemble this because you cannot specify RDI and RSI. They are implicit. But the disassembler wants to be helpful to you and show you what's being done here. In other words, I can disassemble this, but I can't pass that back through an assembler and get the same code out. No operands, 0, 1, 1, 2, 1, 2 or 3, and 3 implicit. All right. Now, here's an example of an instruction that has a lot of implicit stuff going on in it. This is the division operator. And what it says, what div rbx up here at the top says, is take the 128-bit integer. Now, you may be surprised by that because rbx is just 64 bits. Well, bear with me. Take the 128-bit integer in the registers RDX, RAX. High 64 bits are in RDX. The low 64 bits are in RAX. So it's 64, 64, 128 bits. Take that 128-bit number and divide it by the 64-bit number in RBX. And store the 64-bit quotient in RAX and the 64-bit remainder in RDX. And we generate an exception if the result won't fit. So think about this. This is a 128-bit number, okay? So suppose I take this 128-bit number and I divide it by 2. 2 is a valid 64-bit integer. I divide it by 2, which means that the whole thing in here just shifts down by one place in the binary representation. So RDX is not emptied out by that, which means if I store a remainder in RDX, I'll overwrite part of the quotient. And so I'll generate an exception to indicate that it won't fit. It's bad. So you have to be careful with this. And often the thing to do, you'll want to divide a 64-bit integer by another 64-bit integer. And the way to be sure you do that without generating an exception is to put 0 in RDX first. So here's a little picture of that down here at the bottom. RDX, RAX, high and low 64 bits. Divide by RBX. Quotient goes in RAX, remainder goes in RDX. Okay, there we go. These are fixed registers. RAX and RDX are the ones that you use. You can't use other registers to do this. The divisor, you can pick. In this case, I used RBX, but I could have used RCX or something else. There are addressing modes. So we've seen several things happening. We've seen instructions that took a register or a literal number or a memory address. And we've seen in some cases an instruction that took RIP plus an offset. So here's the instruction pointer, add this offset to it. So x86 arguably has 4 different modes for its operands or its arguments to come to us in. Immediate means you just write the argument right there like 7. Register means you just write the register there like RAX. Memory is what we've been seeing in those square brackets with one exception. Square brackets. So we'll see, for example, RSP minus 8 or RSP plus 16. And we'll look at that later on. That can be fairly complicated. The very first instruction we looked at, the one that had the huge list of things to do, it had a fairly complicated memory expression in it. RIP relative, we've seen that. It's RIP plus some fixed offset. We've seen that a couple of times, and that's in square brackets as well. So those are basically the 4 modes. Depending upon what you consult, it will have more addressing modes than this, but those are really the 4 that matter. If you want to learn more about it, you can go read the Wikipedia article about addressing modes, but you don't have to. The immediate addressing mode is obvious. Stick an immediate value right there. So here, this move has 2 operands. The first one is an immediate operand. The second one's an immediate operand. The first one's a register. Here is one that's both registers. Here's one that's a memory reference. I take RDX and I add an offset of 16 to it. I go and get the contents of the location, right? So RDX holds a 64-bit value and memory addresses are 64-bit values. I add 16 to that value. That gives me a new memory address, and I go and I load the 8 bytes at that address into RAX. And then finally, here's a way of doing RIP relative referencing. This says I want to address the location message, which is probably something within my program, but I want to do it relative to RIP, relative to the instruction pointer. This is a way of doing position independent code, and we'll talk about that quite a bit in a future class. So here's some thoughts on writing assembly. Take them for what you will. Here are the tools you have when you're writing an assembly program. You've got operations, and there are lots of them. It's a rich set of operations. You've got registers that you can put stuff in and store stuff in and move stuff around in. But you share those registers with everyone you're playing with. All the code you call, all the code that calls your code, they're all using this. You're all using the same register file. So you have to be careful that you don't overwrite each other's work. Right? You're all working together on the same piece of paper, and you've got to choose the portion of paper you want to use. There's memory. There's stack. You have a stack, typically. You also have a kernel stack. We won't worry about that for a long time, but you definitely have a stack. You have conditional branching and unconditional jumps, and that's pretty much everything you have to create your programs. Right? You can give operations, put stuff in and out of registers, in and out of memory, on and off the stack, etc. Lots of tools don't exist, at least not directly. While loops, if-then else, subroutines, complex data types, and objects. There are proto-versions of these that exist in some assembly languages. Not every assembly language will have nice support for this. x86 has some support for subroutines. It's pretty bare bones. Some languages, some assembly languages don't even have that. And you sort of have to make it up yourself. And that's okay. Loops, x86 has sort of a loop thing, but again, it's real bare bones in here. Okay, you can build all these yourself out of the little Legos that you're given by the assembly language. That's what the compiler does, and you can do what the compiler does. You can build these higher level types out of it. So assembly languages predate high-level languages, but they also come after high-level languages. So they both influenced high-level languages and were influenced by high-level languages. They exist in this symbiotic relationship, obviously. Some of the most influential languages on modern processors, some of the highest influences of the modern processors, are RISC. RISC is incredibly influential. So you may be wondering, why am I saying RISC? When we're looking at a CISC processor, the x86-64, which is a VLIW, right, very long instruction word type of processor, it's because under the hood, the x86 has been heavily influenced by the RISC processor. In fact, it's arguable the x86 is really just a bag of little tiny RISC processors networked together to do their job. Very influential languages. BCPL, one of the most influential programming languages ever. If you don't know about it, you might read about it because you are writing a dialect of BCPL today when you write almost any programming language. C, obviously, and C++, obviously. And vector operations, right? The world is parallel. We like to be able to do things with vectors of values all at once. And that's been very influential on modern processors. That's why we have things like the AVR512 and some of these larger registers is in order to vectorize operations. And if you take that to the extreme, you wind up with these graphics cards that have very large vector processing units in them that can do massive numbers of vector operations per second. The objective function for all of these, for compilers and so forth, is always performance. It's never readability or maintainability, compatibility, usability. And usually the thing that we're trying to optimize is the performance of the compiler, not necessarily the code, right? We're trying to make the compiler run faster, with the idea being that the compiler, when it has more time to operate, can spend more time making your code fast, but maybe not. But that's the important thing to keep in mind, is the objective function is performance. There are trade-offs, certainly. I had to balance a lot of concerns as the designer of an instruction set architecture. And so we have two major strains. We have the complex instruction set computer. With a rich instruction set, typically instructions can vary in length. So you can have very common instructions have only be a single byte or maybe 2 bytes. And less common instructions can be longer because they're just less common. And so you have variable length instructions. The CDC 6600 is an example of this. The Z80, very influential processor, which dominated for a long time, and then the Intel x86. RISC is sort of the other side of the coin. We want to have small instructions. Each instruction does some simple task and typically executes in a single clock cycle. So at the top, we're saying do it as much as you can with a single instruction. At the bottom, we're saying do as many instructions as you can with a small number of clock cycles. In this case, do 1 instruction per clock cycle if you can. These are often fixed length instructions, and you can see why from the example we saw earlier of decoding an instruction and pipelining it. This makes pipelining work beautifully. I just fill my pipeline. All the instructions are the same length. Unless I hit a branch, you can keep going forever, and that's great. IBM 801 is an example. The RISC-V, which is an open source architecture, is another, and ARM is one of these. And ARM typically has 32-bit instructions. There's a thumb mode, which has 16-bit instructions, but for the most part, you can think of it as 32-bit instructions. Here's some references that you can use. I like Felix's x86 reference at the top. I think it's a great reference. It's got a little star by it because it's really good. The official Intel developer manuals are next. If you want to get it from the horse's mouth, go there. But, again, it's the horse's mouth. The next one is the online disassembler. This is a really cool tool. And we'll talk about some other online tools that are really neat, too. There's an online NASM IDE. Ryan Chapman's blog post on the x86-64 system call table for Linux is exactly what you want. That is so great. It's better than almost any other reference on the Linux system calls. So by all means, keep track of that. And then there's the Chromium OS Linux system call table, which is a little different and can be a little confusing. Stay with the Ryan Chapman one and you won't go wrong. Learning assembly, well, even the x86 one, will really prepare you to learn any assembly language. It's really the same set of things, just packaged differently and with sort of different optimizations. When you first go from, let's say, x86 to ARM, there's going to be a bunch of things that bombard you with the differences, and it's a confusing way of doing things. But you'll rapidly find it's the same basic stuff. It's bitwise operations, and the differences are, for the most part, cosmetic. Instead of just loading a 64-bit value into a register, which I can do directly on the x86, I have to load it in pieces or load it indirectly in ARM because, again, they're fixed with instructions. 32 bits is just not enough bits for me to put a 64-bit literal value in. Okay, that's what we would call accidental complexity. It's not essential complexity. The exclusive OR instruction on ARM is EOR as opposed to XOR almost everywhere else. Okay, again, accidental complexity as opposed to essential complexity. So learning one of them really gets you all of the essential complexity in your brain, and then you're prepared to learn more. So let's talk about writing assembly just directly. And the best way to think about that is to go and write some assembly. So writing assembly is going to help you understand it, and it's going to give you a much better ability to read it because you can look at it and think, why are they doing that? And how would I have done that? And maybe, thinking about how you would do it, how you would write it, will help you understand what you're seeing. Reverse engineering can benefit from making changes to a compiled program, right? Again, go back to that example. You're constantly having a hard time at this one section of a video game like Baldur's Gate, and you want to modify it. There's no source code. You need to go in and patch the binary, which means you need to write some assembly to do that. And so that's what you'll need to do. And so you need to understand how to write assembly to do that. And it's fun. It's fun to do this stuff. Programming is fun. Instruction set architecture, ISA. Here's the programming model for you working with assembly. And you'll see this again and again. So up here at the top, we have the processor. The processor provides some stuff. It provides the general purpose registers that we've seen already, like RAX and RBX. It provides operations, add, sub, so on in here. And it has a flags register. In addition, it maintains an instruction pointer and a stack pointer. And those point out into your program's address space. So your program has its own address space. Every process in Linux has its own virtual address space. It looks to it like it has the entirety of memory all to itself, right? Because it's virtual. Memory is virtual. And so your program occupies a chunk of this. The instruction pointer points somewhere in your program, we hope, because otherwise you'll have problems. Following your program is a heap, which grows upward in memory. We get longer as you malloc or allocate more space. The end of the heap is pointed to by something called the program break. Though the program break is not, the arrow doesn't go up here into the processor. It's not maintained by the processor. It's maintained by the operating system. And then there's a stack up at high memory that grows downward toward your program, and that's kept track of by the stack pointer. So in each case, as we've made a decision about where to have a pointer, we have chosen to move the pointer to the right. So the instruction pointer doesn't point to the current instruction, it points to the next instruction. The program break doesn't point to the last part of the heap, it points to the next open address. And the stack pointer doesn't point to the first open address, it points to the last item on the stack. In every case, we've moved it to the right to a higher address. You'll notice we didn't use the very lowest memory here because memory at address 0 is the null. We didn't use the very highest memory. That's typically done, use that for something else. And that's okay, right? It's not like we're wasting memory. This simply doesn't exist. It's virtual. So for all we know, the first address in the heap might be literal physical address 0. We don't know. It's just chosen and maintained for us by the memory management system, which does it all virtually. But this is your programming view, right? I've got an instruction pointer in my program, a stack pointer in my stack. The operating system provides a program break, which gives me some heap. And that's important because, again, memory is virtual. I can't write into an address here in the middle because it just might not exist. It might not be mapped to any real memory. Okay. Let's talk about the x86 architecture. It started out in the world as a 16-bit architecture, which could address 2 to the 16 or 64K. And so you had some 16-bit general purpose registers, an accumulator called AX, a base register, BX, a counter, CX, a data register, DX, then a stack pointer, a stack base pointer, a source and destination pointer, and an instruction pointer. All 16 bits because that's how big memory was. And the neat thing about this is a very rich set of registers. Many processors at the time had far fewer registers. I mentioned the 6800 earlier. It had a B, and an index register initially. And I think later they added a C register to it. Not a lot of registers to work with. These 4 registers, the general purpose registers A, B, C, D, X, are high and low byte addressable, meaning I could look at either byte of the A register. AH was the high 8 bits, AL was the low 8 bits. So I could say AL gets 6, and that would put 6 in this low 8-bit spot of AX. This is called register aliasing, because I'm just referring to a subset of the bits in the register by this name. And we'll see a lot more register aliasing as we add bits to the processor. 8 bits was a byte, 16 bits, or the word. Right? Typically, the idea is a word addresses a full location in memory. We're going to lose that almost immediately because we've chosen to use 16 bits for a word, but that's the way it's going to be. This is not universal. So if you're in the network world, you may see 8 bits referred to not as a byte, but as an octet, right? 8 things together, an octet. So network octets are bytes. You may see 16 bits referred to as a half word, and you will because you'll use the GNU debugger at some point. And so 16 bits here is a word, but elsewhere it might be a half word, so on. Some old stuff actually calls it a double byte or a D byte. We will hopefully never see that again. So while we all agree that 64K should be enough for anyone, it turns out it's not, and we needed to have more bits. So because of base 2, we just double it, right? You add, you double it to now 32 bits. 32 bits lets you address 64K times 64K, or 4 gigabytes. That's great. That should be enough for anybody. And so now we have extended, so you have the E here, extended versions of AX, BX, CX, and DX. So these are all 32-bit registers. Here's our stack pointer and our base pointer. These are pointers. There are 32 bits because memory addresses are 32 bits. Here's ESI and EDI, and here's our instruction pointer, also 32 bits because memory addresses are 32 bits. So SP and IP still exist in this world, but they aren't anything, right? SP is just the low 16 bits of the stack pointer. It's not the stack pointer. IP is just the low 16 bits of the instruction pointer. It's not the instruction pointer, right? And we don't want to use these ever because they won't give us the right thing. Stack pointer is ESP and the instruction pointer is EIP. There's even more aliasing now than there used to be. For example, EAX. I can still use AX. AX didn't go away. It's the low 16 bits of EAX. So if I have a value in EAX and I assign to EAX, I overwrite the low 16 bits of EAX and I leave the top 16 bits alone. And I still have the byte addressing, so I can address the bottom 2 bytes of EAX directly and overwrite them and leave the top 16 bits unchanged. We have to have a new term for 32 bits, and that term is double word, or D word. So you'll see D word a lot, and it's just double word for 32 bits. In some platforms, you'll see word here and half word here. For example, if you use GDB, that's what you'll see. For the most part, word is 16 bits, double word is 32 bits. Well, clearly 4 gigabytes is enough for anybody, but it turns out, no, it's not. So that led to a couple of things, one of which we'll sort of ignore, which was Intel's 64-bit architecture. The Itanium, which you can look up, it's an interesting historical footnote. But it also led to AMD's 64-bit extension. That's why we call the AMD 64 architecture, or the x86 64. We just take what's there and double the bits again. So now it starts with R. You can think of R as register, R for register, and we have our 4 general purpose registers. We have a stack pointer and a base pointer, source and destination, and an instruction pointer. You still have ESP. And a common mistake that people who come into this world from the world of 32-bit programming is they'll sometimes use ESP. And when they do, they'll get seg faults. And they'll say, why am I getting a seg fault? I don't understand what's happening. Well, ESP is not the stack pointer. It's just the low 32 bits of the 64-bit stack pointer. And that's important because the stack pointer exists at high memory, so you need all the bits. Same thing for EIP. It's RIP now, RIP. In addition to these, we finally decided that, we need more registers. We just need more. And here they are. And we call them R8, 9, 10, 11, 12, 13, 14, and 15. What? Well, here's 0, 1, 2, 3, 4, 5, 6, and 7, not counting RIP. So some assemblers let you refer to them that way. Almost none want to do that. But that's what they are. And so these are the next 8, giving you a total of 16 general purpose registers plus the instruction pointer. There's even more aliasing than there used to be. RAX is now a high 32 bits plus EAX, a name for the low 32 bits. AX is a name for the lowest 16 bits. And you still have these, which let you reference the bottom 2 bytes of RAX. They all point to the same storage. They are aliases for the same 8 bytes of storage inside the processor. So 8 bits is still a byte, 16 is a double word, 16 is a word, 32 is a double word. We need something for 64, and we call it quad word. There you go, Q word or quad word. So others will call this a giant. I don't know why. GDB does that. But it's byte word, double word, and quad word for us. There's, of course, even more that I have not talked about. So I've talked about the registers up here in this general purpose registers piece. I haven't talked about the floating point registers, right? These processors used to have coprocessors that dealt with floating point. Now that's integrated in the processor itself, and you have 80-bit registers, and those are 80-bit floating point registers. You also have 64-bit MMX registers. So there are 64-bit registers up here, but in addition you have MMX 0, 1, 2. These are the low 64 bits of each floating point register. So I could set FPR 0 to some value, and then if I think I can set MMX 0 to some other value, I can't, because I'll overwrite part of this, right? So these are all one thing. This is just an alias for, this is just an alias for the low 64 bits of this register. In addition, there are 128-bit XMM registers. So it's not at all confusing that we have MMX and XMM, but we do. 128-bit XMM registers. We also have the XMM2 series registers, which are 256 bits, and we have the AVR512 registers, which are 512 bits. And there are some versions of the processor that have even larger ones. We don't need to get into that. There are segment registers. So remember how 16 bits was enough for anybody? It turns out it wasn't. Well, one solution was to double it. But how about if instead what we did was we let you use 24 bits by just shifting them a little bit. So that was the purpose of the segment registers. The segment registers told you which memory segment you were referring to, and then you used a 16-bit address within that memory segment. Now wait, you're saying, hold on. How wide were the segment registers? They were 16 bits. Now you're saying to yourself, well, 16 bits plus 16 more bits is 32 bits. Why isn't that a 32-bit address? It's not. You shift it a bit and then you add them, and that's just how it worked. Segmented addressing seems weird to us now because it is simply weird. And so we typically had a code segment that pointed to the segment that held the code. And how big was that segment? Well, 24-bit address minus a 16-bit offset gives you 8 bits. So you had an additional 8-bit space that you could shift around by and choose your base as. And so the code segment was where your code was. The data segment pointed to your data. Stack segment pointed to your stack. And you had these additional segment registers, E, F, and G, that you could use to point to other segments. When the 286 was introduced, it added these. So these weren't originally present. They got added by the 286. The 286 was an interesting processor historically because it was the first processor to have a protected mode. And Like with the first version of most things, it had problems and issues, and we're going to ignore the 286 because really it did not carry on. Nothing is really backward compatible with it, so just nothing's. It's one to forget. The 386 established the new protected mode, and that's the one we carried forward with, and it added the F and G ones as well. So we started out. Didn't need all of these. We had 16-bit addresses. That's all anybody ever needed. We added segmented addressing. Then we added additional registers, and life was good. So for the most part, you can ignore the segment registers in your programs. You'll still see them in disassembly sometimes. They are still used. The current privilege level is found in them, along with some other stuff. But for the most part, you don't need to think about them anymore. People will say they aren't used anymore. It's not true. They are still used, and you can still do stuff with them. But for the most part, in this class, at least, you can ignore them. Flags. Well, we need flags. We need a carry flag to tell us we need to carry or borrow. A parity flag, which when there's even parity, when there's an even number of ones or zeros in something, it's set to 1. People have asked me, is it an even number of ones or an even number of zeros? It's either, right? There's always an even number of bits. So if the number of ones is even, the number of zeros must also be even. If the number of ones is odd, the number of zeros must be odd. So it's either one. We either have even parity, which we represent with a 1, or odd parity with a 0. Seems backwards, but that's the way it is. Just think of parity as indicating whether the parity is even. The adjust flag is a 4-bit carry. It's a carry from 1 nibble, 4 bits. That was important in the past. It's not so important today. In fact, it's getting increasingly hard to access this flag on the 64-bit processor. A 0 flag to tell us if the result is 0. Sign to tell us if the result is negative. The trap is a way of single-stepping the processor. When we look at how GDB works, we'll see the trap flag. The interrupt flag, the direction flag, which is used for string operations, the overflow flag, which tells us if we overflowed, and that's different in a subtle way from carry, and we'll talk about that when we talk about it. And then there's a privilege flag that we'll, for the most part, just ignore. When we went from the 16-bit to the 32-bit world, we got the E flags or extended flags register. There's a resume, a virtual 8086, an alignment check, an interrupt pending, a CPU ID, which caused a lot of controversy and consternation at the time, and virtual address descriptor. Those all got added into the 32-bit extended flags register. You can assume, you can easily see what's coming next. We're going to double it again, and we'll have an R flags. And we do, in fact, do that. We have an R flags register, but as you can see here at the bottom, we didn't really need anything else, and so that's all just reserved. R flags is, in fact, a 64-bit thing within the processor, but only certain parts of it are actually used. So, and you can see our old E flags, our old flags and E flags are up here, right? The first 8 bits are really important. The rest have some use. And then we have some stuff down here we don't need to worry about very much. How can I get access to this? Well, I can get access to it in a couple of ways. Push F, the push F instruction, that's the mnemonic for it, pushes the flags register onto the top of the stack. What is flags? It is this part right here. Okay? This is flags. It pushes that onto the top of the stack. Not E flags and R flags, just flags. Pop F loads the flags register from the top of the stack. So suppose I want to explicitly set the adjust flag, which I can't get to many other ways. I can do a push F. I can exclusive OR it with hex 10 to set that flag. And then I can do a pop F to put it back into the flags register. And now I've set the adjust flag. Same method for testing it, etc. We have similar instructions for the E flags. We have a push FD and a pop FD. And there's a push FQ and pop FQ for the quad word version of this to get all of our flags. I mentioned before that the first 8 bits, 0 through 7, are really important. They're so important that load AH from F will put the flags into AH. So we'll put the first 8 bits of the flags in AH, which is just a byte, right? It's the second byte, second lowest byte in RAX, and it puts the flags in there. Save AH into flags, puts AH into the first 8 bits of the flags register. RIP is the instruction pointer. You can't directly access it. So you can't just say, go get the contents of IP and put it in RAX. That won't assemble. Cannot do that. But you can use it in a variety of ways. And there are tricks to read it during execution. In fact, reading it during execution is an important trick that we'll see later on. Now, the stack pointer is a general purpose register. You can use it like you use anything else. You could write code that pretended there was no stack, never did anything with the stack, just never used push and pop, and you'd be fine, and you could just use RSP to do whatever. But that's not how code's going to work on this processor. We're going to need a stack because the OS expects you to use the stack, and everybody else does as well. And so we want to use the stack, and that's RSP. You'll often see us doing explicit math with it, like subtracting from RSP, which is a way of reserving space on the stack. Adding to RSP is a way of deallocating space on the stack. A common mistake is to use ESP in place of RSP. Don't do that. Just pretend ESP doesn't exist. The base pointer is RBP, and it is often used to point to the current stack frame, the base of the current stack frame. You don't have to do that. Some code we'll look at won't do that. So it'll use it as a general purpose register. But a lot of code that we'll write and look at will use it as the base pointer. We'll talk about what a stack frame is later on. There's a counter register, RCX. Again, general purpose register. You can do whatever you want to with it, but it also has some special meanings that other instructions don't. There are conditional branches that look at RCX to determine whether to branch, and there are special instructions like loop that depend on the content of RCX. So it's an implicit register used by them. Source and destination are used by the string instructions, source and destination, and often they're used that way by other code. When you have a source of something and a destination, you'll often want to use RSI and RDI so you can keep it straight in your head what you're doing. They also rely on the direction flag. If you think about copying a chunk of memory to a new location, if those chunks overlap, you may want to copy from the back or from the front, and then things will work. If you do it the other way, you get a mess. The direction flag controls the direction in which things like that happen. And here we go. So we're going to create an assembly program, and we'll just start up and exit. And this is it over here on the side. Don't worry about what all this stuff means. We'll go through all the parts of it later on. This is just our basic startup and shutdown assembly program, ex1.asm. What we do here is we call exit. This is how you call exit in assembly, and this does the exit system call, and then we're done. That line up at the top is what will build it. So we're going to assemble it, and then we're going to link it using LD, and that's it. So make AS would expand to this, and you can just type this on the command line yourself, NASM-F ELF64 EX1ASM, and that will assemble this using NASM, the net-wide assembler. Now, what happens? Well, the assembler looks at our code. It sees that this is a move instruction. It looks to see what the operands are, and it finds that they're RAX, which is a register, and 60, which is an immediate value. And it figures out how to encode this as machine code bytes. And it may not do it the way you expect exactly, but it will do something that will have the same effect as doing this. And it writes out those bytes. Then it looks at this line of text, and it tries to encode that as machine code. Then it sees syscall. It just looks that up and includes those bytes. And it sees halt and it includes those bytes here. The stuff over here with the semicolons, those are comments. They are not processed by the assembler. Once it's done all this, it has produced an object file which ends in .o, the same as if you compiled but not linked your C program. So we can take a look at what's in that object file, and the way we do that is using the tool we mentioned before, which is objdump. So object dump, -D says disassemble, -M Intel says use the Intel dialect, and that's important. It'll have all the little funniness of the AT&T dialect, and we'll give it ex1.o. And it will tell us some things. It'll tell us first, it recognizes the file format. Objdump can examine a lot of different object file formats. So the first thing it has to do is figure out what are we giving it. And it figures out this is a file that's formatted in the ELF64. That's the container format. For x86-64, that's the processor. So this is the binary file structure, and this is the processor itself. If I were on a Raspberry Pi, I would, on the most recent one, I'd still see ELF64 because the most recent Raspberry Pis are 64 bits. Raspberry Pi 4, let's say. But I'd see a different processor over here. I'd see the ARM V8, I think. I can't remember. So I see something a little different. Then we get this assembly of this section text. Don't worry about that. We'll talk about sections later. And here's what's in it. It's the stuff in red here. It's got these 5 bytes and these 5, these 2, and this 1. So these 5 are this first move instruction. These 5 are that second move instruction. These 2 are the syscall, and this last one is the halt. There you go. So you can see it's disassembled over here. And so you'll notice a few things have changed. Instead of 60, we are showing hex 3C. Hexadecimal is unbelievably important to reverse engineering. You'll see hex all the time. What is 3C? 3 times 16 is 48. C is 12. 48 plus 12 is 60. So there you go. What's this stuff at the start? Well, this is the offset. So the assembler doesn't know where things will ultimately go in memory. So all it's done is what I told you. It's converted these into the machine code representations. And it, by default, started at address 0. And so this offset 0 is B8. And then 1, 2, 3, 4. Offset 5. 6, 7, 8, 9. 10, which in hexadecimal is A. 11, 12, which in hex is C. There you go. And as I said before, we'll talk about sections a little later on. So now we need to link our program. So programs can reference pieces of other programs. They can reference, your program will do that, right? It will, if you write your program and it references printf, you have to go find a definition of printf somewhere so you can call that code. And linking your program together with other code that contains those definitions, that's the linkage problem. And so the linker has a few different tasks to do. It has to figure out what the addresses of things are going to be. We go back one. Here, the assembler just said, I don't know, I'm going to put stuff at 0. 0 is not a place I can put a program because 0 is the null pointer. I'm not going to put my program at 0 every time I write a program because then I couldn't have 2 programs work together. They'd overlap. So the linker has to figure out where to put things, and it gives everything an address. In addition, it has to figure out where important symbols are inside your program and connect your program with important symbols in other programs. And that's its job. And we'll talk a lot more about the linker later on. But to link it, this $make_ld expands into something you can type yourself, which is LD, which is the name for the linker, -O, and then the thing we want out, which is ex1, and then all the things we want to link together. In this case, it's just one thing. It's ex.o, and we'll link it. When we do that, we get a warning. It's just a warning. It says it can't find the entry symbol _start. It's defaulting to this thing right here. Well, this turns out to be the address it's assigning as the first address in our program. So it's going to assume the first instruction in the stuff we gave it is in fact the instruction we want to start with. We can specify to start somewhere else with this start symbol, and we really should include a start symbol, but since it couldn't find one, it made the reasonable assumption that we just start at the first instruction. So let's try it. We run our program just like that, and if we put a semicolon, echo dollar question mark, we can see the return value from our program, and that's going to be this right here. So RDI is going to hold the return value. You can edit this and put another value in here, and then you can link it, you can assemble it and link it and try it again, and you'll see a different value come out here. You should do that. It's a fun little exercise to be sure everything's working for you. We can look at the binary with objdump, and we'll see things are a little different. Again, objdump tells us it recognizes the file format. It is an L64 for this. It tells us it found a section. And then we see all the little pieces down here at the bottom. Sorry. And I'm going to move forward one. And we're going to compare this side, which is what the assembler gave us, to this side, which is what the linker gave us. And you'll notice we have B83C000, B83C000, have the same bytes, raw bytes for the instructions, but we have a different address. Over here, the assembler didn't know the address. Over here, the linker does. It's assigned an address, and you can see now these are actual addresses here. But it looks very much like the offsets over here. Here's a second example. Let's go ahead and fix, and this, all this example does is fix our missing start symbol. So right here, this is assigning a location a name. So the location here will be the first byte of the first instruction. So we're giving this location a name. This is just like a target symbol in your C program. You can have labels in your C program that you can use with goto. It's not widely discussed, but if you look at the source code for the Linux kernel, you'll find lots of gotos. It's a very common way to write certain types of embedded code. We'll talk about the advantages and disadvantages of that at some point, maybe if we have time. So here's a label, represents this location, underscore start. That's great, because now we're explicitly telling the linker, I want you to start here. This is my code on entry. Now, when we link it, we get the same warning. What's happening here? Why we put start here? There's the start symbol. It has a start. Can't find it. It's the first thing in the file. Well, by default, labels are private to the module. We don't want this to be a private label. We want this to be a public one that the linker can see. Okay? It's kind of the opposite of C. In C, labels are public by default. You make them private by using the keyword static. Here in assembly, labels are private by default. You make them public by using the keyword global. So let's do that. So we'll add global underscore start. The indentation is not important here. Global underscore start. Now this is a global symbol. When I assemble and then link, I get no warnings. Still everything works. Great. So remember that if you want to access a symbol from outside, from another piece of code, external to it, or pass something to the linker, you have to make it global. There's homework. It's due on the 31st of August, and the homework is available online in iLearn, but it's also, I want you to take this. What is all this? To find out what this is, I want you to go and read about XXD. XXD is a little utility available under Ubuntu. I believe it's installed with binutils, and it has to do with creating a hex dump of a binary file. And you can read about what it does. And once you've read about what it does, I want you to take this and turn it into a binary file and run it. And once you've run it, I want you to take just the output and only the output in a text file. Don't take this and embellish it and make HTML and then build it. Don't do any of that stuff. Just the text output and only the text output of this in a text file, and upload that as your answer on iLearn. Okay? I'd recommend you look at it with objdump and with readelf if you spend a little time with that to see what you can see. But that's not part of the homework. The homework is just to get the output of this thing and put it up there and figure out how to do that. And that's it.